Так, ну, коллеги, давайте мы начнем, потому что у нас и трансляция идет, и многие ко времени собираются подключиться, посмотреть наше мероприятие. Значит, сегодня у нас кристаллохимический совместный российско-китайский семинар, на котором приехали уважаемые гости из Китайской Народной Республики, Шили Пань, значит, профессор, замдиректора Института физики и химии Китайской Академии Наук, и, значит, Чихуа Ян, тоже профессор, как бы, она представляет заведующую лабораторией численных методов оптоэлектронных материалов, и у них сегодня два доклада. Значит, вчера они выступали в Сколково, сегодня они выступают в Московском университете, поэтому, ну, я не знаю, Елена Леонидовна, вы сделайте несколько комментариев, как бы. Okay, let's switch to English and.
I may add only very short comments. Our friends are young. They are working very active, and practically in the last 10 years, they produced huge amount of publication, new structures with properties and without. And their scope is close to us, and because of that, we have a common interest, and we follow our publication and their publication every time. They have very high indexes in citation, in our Hirsch and so on. They have very many grants, and it seems to me that this group in that institute is one of the most productive in the world, really.
Okay, thank you very much. I'm very glad to stand here. I'm very excited to visit Moscow State University. In fact, as we know, Russia is a metropolitan country. Yeah, it's very significant in the world, especially in the recent years. Especially maybe today, President Putin and President Xi Jinping, yeah, stay in China, either in Qingdao City, have contract maybe make close relationship between Russia and China. So it's my great pleasure to stand here to report our research about rational design and the synthesis of new nanoparticle materials. My name is Shi Pan, coming from Xinjiang Technical Institute of Physics and Chemistry, China Capital Sciences. My institute is situated here in northwest of China. Here, it's very close to Moscow, very close. 6 hours from our institute to here. So my talk is mainly divided into 3 parts. The first part is about background. As we know, in 1960, scientist Mayman invented the ruby laser. 1 year later, Franklin and his co-workers firstly observed the nanoparticle effect. After that, the search for new nanoparticle materials became the focus of research. So after that, there are many applications for the nanoparticle materials. For example, they can be used as semiconductor, photolithography, laser medicine, and laser communication, and the laser micromachining. Of course, in the laser system, nanoparticle materials are the key material for the solid state lasers. So, according to the wavelengths, we can see in the visible region, the scientists invented many nanoparticle materials. Of course, Russian scientists also gave great contributions to nanoparticle materials. In this region, the materials satisfies the requirements in our life. But for the infrared region, there are several nanoparticle materials. However, due to their low layer damage threshold, so these kind of materials cannot satisfy the requirement. For the UV or deep UV region, the scientists in the world invented many materials. However, with the development of society and economic, these materials cannot satisfy the requirement in our life. So the scientists want to search for new materials. According to the regions, for example, the scientists invented these several materials. These materials have been commercialized in the world. For example, KTP, LBO, BBO, CLBO, KPBF. In fact, this material was invented by Russian scientists. It's a very famous material. This material is the only one material can output the 6 harmonic generation of Nd:YAG laser. It means it can output the deep UV laser wavelengths. However, this material contains highly toxic beryllium and shows a layer habits. It means it's difficult to get a large zinc crystal because the layer habits. So the scientists in the world want to search for new material. However, it's difficult because we should balance the 3 factors among SAG response and bifurcance and by a band gap. In fact, it's difficult to balance these 3 factors because, for example, for band gap and SAG response, they are inversion proportional. It means it's difficult to balance. In fact, for the material should have the, for example, for the UV or deep UV nanoparticle materials, the UV cutoff edge should be less than 200 nanometer. For the material is SAG response, in general, larger than 1 times that of KDPC. And those materials should have suitable bifurcance for phase matching. Of course, the material should be easy to glass in crystal and do not contain toxic raw materials. So in the world, scientists want to search for new material, use different strategies to design materials. For example, the scientists use second order Rangtala cations, want to get a large second harmonic generation. For example, very famous material, BIBO. Yeah, this model indeed have a large acid response. However, its UV cutoff edge redshifts. And also, another group want to introduce beryllium to remove BO3 dangled bonds because they want to make the deep UV cutoff edge blue shift. So they're successful. It means, for example, Capi family, this kind of material have a short cutoff edge large below 200 nanometer. However, this kind of material contains toxic beryllium. And also, there are many scientists want to design the material with large bifurcance. They use pi conjugated BO3, CO3, NO3 triangle units because these kind of units can produce large bifurcance. This kind of material, for example, KBF and AbCO3F, this kind of material indeed have sufficient bifurcance for phase matching. However, these kind of materials have strong layer tendency and is difficult to glass in crystal. So it means all those scientists use different strategies to have large acid bonds, have cutoff edge and large bifurcance. However, it's still a challenge to balance 3 factors to design an ideal UV or deep UV nanoparticle materials. So our work faces the problems, want to search for new UV or deep UV materials. The next is our group results. We can choose these results. So first step, we want to, based on the database scientists research in the world, we want to search for the accent genes. We want to search for the accent units to design the new materials. So, in fact, we found the basic units. For example, this kind of material have the UV or deep UV cut-off edge. And also, we analyze the relationship between structure and properties. For example, we analyze the punctuation and the connection, because this kind of style can produce a large acid bonds. For example, the scientists remove down bonds, use tetrahedral units. For example, Pu4 want to have the material with short cut-off edge. And also, the scientists use the structure with preferred orientation units, and also use perfect strike-like structure. This kind of structure I want to emphasize. In fact, this material was found by Professor Barkonova. This material is very interesting because this material has perfect structure. As we know, perfect structure is a very famous structure. It can produce large acid bonds. And also, it can produce suitable bifurcations. So after our systematic research analysis, we found in this region, the materials can have large band gap. It means its band gap is larger than 6. And its acid bonds is larger than 1 times that of KDP. And also, we reviewed the discovered metal borates and analyzed the current structure. We want to search for fluorine-containing borate. In fact, for fluorine-containing metal borates can divide into 2 types. The first one is the fluorine atom connect with metal cations directly. This kind of borate named borate fluoride. For this kind of material, the units, the fluorine is connected directly with boron. It means this kind of units is called fluorine oxoborates, or simply called fluorine borates, such as KBF, LBOF, and etc. In fact, the scientists have investigated that fluorine is incorporated into a system. The compound will have deep UV cut-off edge. For example, scientists want to substitute hydro OH by fluorine atom. They found UV cut-off edge of BiBOF is 50 nanometers shorter than that of BiBOH. It means the fluorine atom is beneficial for large band gap. And also, we also prove that the fluorine atom is also beneficial for producing large second harmonic generation. And also, we proved that the fluorine atom can give indirect contribution and direct contribution. And also, we want to get with material have the large bifurcations, because the bifurcations is large, it can produce the shortest UV cut-off edge, UV laser wavelengths. For example, from this table, we use a DFT calculation. We found in traditional manner for BU3 is a very excellent genes because it can produce large acid bonds and the large band gap. For after we substitute oxygen by fluorine, we can get these 3 units. These 3 units have very excellent properties. It can produce large band gap and large bifurcations, large acid bonds. It means these kind of units, these kind of genes may be a best candidate for design new materials. So after our analysis, we determined the system For example, we want to use alkaline earth metal as a cation because these cations have no DD electron transition in the UV region or deep UV region. And also, we want to use boron oxygen groups as the anions because these groups can produce large band gap, especially for BU3 group is beneficial for large acid bonds and moderate birefringence. Of course, we want to use fluorine atom to adjust the crystal structure because fluorine atom can bullshift the cutoff edge, can generate large distortion and large acid bonds. And also, the material have increased optical anisotropy and birefringence. So it means fluoroxyborates maybe is the best candidate as the beryllium-free deep ultraviolet nanoparticle materials. So we use LBO, lithium borate. It's a famous UV nanoparticle materials. We want to substitute oxygen by fluorine atom. So get the several compound. These compound we can see the fluorine atom may be like scissors. It can cut through the fixed three-dimensional network. It means the structure can maybe the flexibility can produce different structure. So we found a suitable candidate lithium fluoroborate. In fact, for this compound, its original compound is LBO, lithium 1, boron 3, oxygen 5. We doubled the formula, lithium 2, boron 6, oxygen 10. We substitute 1 oxygen by 2 fluorine atom, the charge is still balanced. So this material, after substitution, we found that this material have excellent properties. For example, it has the suitable birefringence. In general, for analytical materials, the birefringence is range from 0.04 to 0.1. So it means this birefringence is suitable. And the predicted use birefringence, we can predict the shortest type 1 SAG wavelength is about 192. It means this material can output the deep UV below 200 nanometer laser wavelengths. And also, this material have a suitable SAG response. Is phase matchable at 266 nanometer. And also, we still want to search for the best, the suitable compounds for produce deep UV laser wavelengths. We want to base on the KPF, want to search for new materials. In fact, we want to substitute BU3F in KPF by BU3F because a moment ago I mentioned this unit may be a best candidate for produce large band gap, large acid amounts, suitable birefringence, and also we want to have the material with better growth habits and higher anneal coefficients. This material doesn't require toxic beryllium. Okay, we found the ABF family. This family inherits the excellent optical properties of KPF and has significant advantages over KPF. Next, I will show you several examples. The first example is ammonium fluoroxyborate, named ABF. This compound crystallized in symmetric group is PNA21. It means this group is non-symmetric. This material has superior property. For example, for this structure is KPF structure. We can see the interlayer space is about 6.25 angstrom. For our compound, we found the interlayer space is about 3.81 angstrom. It means the interlayer is shorter than this in KPF. So it means maybe it's easy to grow large crystal. And also in the intralayer, it has a double the BO3 density. Because in general, in the interlayer, if the density for the BO3 group is larger, it will produce large acid response. So next step, we try to grow small thin crystal. From the detail we can see, the crystal has no layer habits. It's block. Yeah, it's very good. So, and also, we also use the crystal to measure the UV cutoff edge, maybe around 156 nanometer. And also, we measure the powder acid response. So we found it has large acid response, about 3 times that of KLPG, or half times that of BBO. And also, we use the crystal to measure its birefringence, and use the birefringence to fit the thermal equations. And we use these thermal equations to predict the phase matching range in XY plane, in YZ plane, and XZ plane. From this figure, we can see the shortest phase matching SH wavelength in XY plane is about 158 nanometer. In fact, from 1960 to now, 58 years passed, only KBF and RBF can produce deep UV laser wavelengths. For ABF, it's another nanocrystal that can generate deep UV coherent light below 200 nanometer by direct acid response. In fact, we covered with Professor Xu with the group in Technical Institute of Physics and Chemistry, China Academy of Sciences, and evaluated the first homogeneity of ABF. In fact, in the world, for the first homogeneous material, it is still absent. So for this material, we can see the first homogenization effect. In fact, our interest want to evaluate the deep UV laser output. So further evaluation may be all in progress. And also we want to give the second example for use cesium substitute ammonium. We got CBF. This compound also crystallized in PA21, same group. However, they shows a very different structure. For example, as we know, for BBO, why BBO can produce a large acid response 6 times that KLP? Because for BBO, there is this unit, B3O6. It means 3 BO3 connected with each other by sharing corners. Get this unit. This unit is very good units. It can produce large acid bonds, large birefringence. For all compound also has the units B3O6. For KBF, for example, they have base units BO3 plus BO3F. For all compound, we have the BO3F. It means this compound inherits the both units, B3O6 and BO3F. And also, this compound, the interlayer space is about 3.96 angstrom. It is much shorter than that of in KBF. And also, this compound also exhibits very excellent properties. For example, we use the crystal to measure its deep UV cutoff edge is around 155 nanometer. And also, we measure its powder acid response. We found its acid response is about 1.9 times that of KLP. And also, we use the crystal to measure its birefringence. Use the birefringence to calculate its shortest set harmonic wavelength. It's about 171.6 nanometer. And very importantly, this compound melts constantly. It means this crystal can be grown from the stoichiometric ratio. maybe we can grow this crystal by Cholsky method, by pulling method, to get the crystal directly. Yeah, from ratifier, this we can got the block crystal, although it's not good. And also, we try to further to search for new compound with maybe with excellent properties. These three compounds are very similar. However, the similar formula, however, they show different structure. For example, the cell gravity is very different, P21, P321, P62C. And also, these three compounds exhibit excellent linear and nonlinear optical properties, including short UV absorption edge, large acid bonds, and also we found another sodium ferroxyborate. This compound crystallized in symmetric group C2. The symmetric group is very different from the previous ones, and also exhibits outstanding properties. For example, it has shortest type 1 phase matching wavelength, is about 166 nanometer. And also, we found another alkaline earth ferroxyborate, strontium ferroxyborate. This material crystallizes in CMC21, and its UV cutoff is much less than 180 nanometer, and shows acid bonds about 1.6 times that of KDP. And also, it has large bifurcations at 532 nanometer, is about 0.07. Its short of phase matching second harmonic wavelength is about 180 nanometer. And also we substitute calcium, surrounding by calcium, we found the ice structure with SPOF. In conclusion, we found this kind of material, alkaline earth or alkaline metal earth, boreas, they choose very excellent linear and nonlinear properties. KPF is the only one material which produces the deep UV wavelengths, laser wavelengths. For our compounds, especially for ABF, it can produce the shortest phase matching acid wavelength is about 158 nanometer. For KBF, it can produce 1C2 nanometer. It means this compound maybe have excellent properties. Yeah. After our paper published, there are many comments. For example, Chemical and Engineering News give comments, promise to further break down the deep UV wall for anneal materials. In fact, for deep UV laser, it is very important for our life, especially for maybe especially for micro machining. For our cell phone, maybe use the deep UV laser. It can produce the better microphone. And also, we also concern the nanometer material, especially in infrared region. Commercially available IR nanomaterial, three compounds. First one is AGP, AGS, and AGSE. These materials have wide application in the world. Only three compounds, three crystals. However, these crystals suffer from two drawbacks. One is low layer damage threshold. The second is it's difficult in lasting crystal, because this kind of material should be grown in closed system, cannot be imposed to atmosphere. So it's difficult lasting crystal. In fact, why it's difficult to search for infrared nanomaterial material? From our system research, we found if we want to get the excellent nanomaterial material, the material should have a critical balance between band gap is larger 3, and acid bonds in general larger 10 times that of KDP. And we found several materials. These materials can balance between band gap and acid bonds. It means these materials have excellent properties. And also, we want to search for new IR materials. These materials can grow in atmosphere and with large laser damage threshold. So we use the following strategies. For example, we use highly electronic halide as anions. We use lead with cations. As we know, lead oxygen have no absorption in mid-infrared region. After that, we found this crystal, POC. This material has very excellent properties. For example, about its thermal property from the TGDLC and XRD technique, we found this material melts constantly. Its melting point is low, it's about 526. And also, we tried to grow some thin crystal. We found that it's easy to get some crystal in atmosphere from stoichiometric ratio melt in the open system. It means it's easy to grow thin crystal. And also, we measure its nanometrical properties. For example, at 1064 nanometer, it exhibits 4 times that of commercial KDP. In infrared region, it shows 2 times that of AGS, IR commercial material, at 2090 nanometer. And also, this material is also transparent over a broad spectral range from 0.34 to 13.9 micron. It means it can cover 2 important atmospheric transparent windows, 3 to 5 to 14 micron. And also, a moment ago, I mentioned the commercial IR material has drawbacks because it has low laser damage threshold. So for this material, we contrast the laser damage threshold with AGS. We found its laser damage threshold is about 12.8 times that of AGS. It means it has very excellent laser damage threshold properties. In summary, we proposed a new functional material of functional units. It means excellent genes, BOF units. These genes can be incorporated into broader system, can produce large band gap, large acid bonds, suitable buffer genes, and also we found the ABL family of promising deep UV nanoparticle materials. In infrared region, we found a new material POC with excellent properties. Next, we want to search for new compound with excellent interesting properties and grow lasting crystal with high quality. Of course, this kind of crystal may be challenging for us to grow lasting crystal because in this kind of system, there are volatile fluorine element. And also for fluorine Boris system, the viscosity is high. It means the particle cannot transport, it cannot grow lasting crystal. So next we want to use high temperature flux method, search for suitable flux and thermal fields, and we want to grow lasting crystal. Yeah. Here I want to thank Professor Zhihua Yang, Dr. Biming Zhang, and Dr. Miu Ding, and other students. And also I want to introduce my group. In my group now there are 6 professors, 6 associate professors, 1 assistant professor for postdoc, plus more than 60 students in our group. In the future, welcome all of you with the China, with the China Academy of Sciences, with our institute, with our group, with the group. Of course, maybe we can collaborate with each other, apply for Chinese national funding, the funding from China Academy of Sciences, with our institute, with our group. And also, in Xinjiang, there are many, many beautiful sceneries. You see, there are many beautiful places. Welcome all of you to visit Xinjiang. That's all. Thank you very much.
Very informative presentation and very interesting and professional. Saying frankly, for me I'm very impressed by the scale, by the number of researchers in your group and students, 60 students. It's really great.
Thank you very much.
Yeah. However, I belong to a mineralogical wing of our community, and therefore let me ask you some general questions. First of all, the main accent in your presentation was made on borates.
Yeah, borates.
Basically, yeah. Oxoborates, let's say, borates. What is the reason, in your opinion, what is the specific features which allow to use borates as non-linear optical materials in respect, if you compare, for example, with other compounds with oxoanions like carbonates? We know that some borates with non-linear optical properties belong to huntite family.
Huntite.
Yes, definitely.
Yeah, very good question.
Yeah. So, but so if I understood correctly, the main accent was made on borates. What are specific structural features maybe which determine the application of these crystals? That's my first question, and then if you allow just one.
Yeah, okay, thank you. It's a very good question. Thank you very much. In fact, for borate system, there are many minerals, many famous minerals found by Russian scientists. In fact, I want to search for suitable candidates in mineral database. In fact, it is very interesting because these materials, in fact, they belong to different mineral types. Yeah, it's very, very important. And also for huntite, it's a very important mineral. And also this material is a very good, interesting property, very excellent property. They can be used in visible region. It's a very, very important non-elliptical materials, especially used 532 nanometer laser, maybe used in blue region, for example, for 92 nanometer wavelengths. It means huntite, this material is very important. It's a very good non-elliptical materials. Another reason for we want to search for non-elliptical materials in borate system. In fact, borate, maybe we know, all of you knows borate, because in borate system, the boron can coordinate to 3 oxygen or 4 oxygen. It means can forming BO3 and BO4. And further, BO3 and BO4 connect with each other, sharing edge or sharing corners to form different units. B306, B307, B309, or B409, and many kinds of units. So it means borate system can produce plenty of various different units. It can form different structure. Only have different structure we can search for. Maybe you can search for suitable compound with interesting properties. So in fact, my advisor, Professor Changtian Chen, is the inventor of BBO, the first non-elliptical material BBO. He told me, Pan, borate is plenty of database. You should search for new UV or deep UV non-elliptical material in borate system. In other system, for example, in carbonate, in nitrogen system, for example, in carbonate system, it's difficult to glassine crystal because we incorporate carbon dioxide into the system, should use the closed system glassine crystal. It's challenging, it's difficult. For example, we use NO3, for example, nitride system to search for material. However, as we know, for nitride system, it's not stable. with the high, we increase the high temperature. So it's not stable in air. For example, in laser, so the temperature is very high, so it's not stable with the compound. So for other oxide, for example, tungsten oxide, or other kind of, for example, titanate, for example, KTP, potassium, titanium, phosphate. This compound is a very excellent property. But this material is UV cutoff edge is about 400 nanometer. For example, for phosphate system, maybe in the next Professor Yang will introduce. Phosphate system may be a suitable system for searching for new UV or deep UV materials. However, it's also challenging. Maybe Professor Yang will introduce this section. In conclusion, it means board system and maybe it's the best system to search for new nonlinear material, especially for UV or deep UV region. Yeah, that's all. Thank you.
I also noticed that the refrigerants, when you substitute
Beryllium by,
for fluoride,
yeah,
is higher.
yeah.
What is the crystal chemical explication of this phenomenon?
You mean we substitute the BO3F, replace the beryllium BeO3F by BO3F, right? Yeah. As we know, for boron atom is coordinated 4 oxygen. We only substitute 1 oxygen by fluorine, forming BO3F. These units, from the DFT calculation, it can produce large acid bonds. It can produce large band gap, suitable by virgins. This units, this gene, maybe is the best gene. Maybe the best gene. Of course, BeO3F is also a good unit. However, as we know, beryllium oxide is toxic. It's difficult to commercialize in our life. Yeah. So this is our goal. We want to substitute, BO3F into the border system. Yeah, like this. Yeah. Thank you. Yeah. Thank you.
I would like to ask simple question. You show very many promising materials.
Yeah. Thank you.
And some of them may obtain a real application.
Yeah.
Do you have already a real patent? Yesterday I heard that you asked, and you have already some materials which is patented, which has some patent, or not yet?
Pardon, you mean?
Do you have already patent for any your promising crystal? Have you obtained already patent for some of your crystal?
Yeah. We got some crystals.
Which one are?
Which one? Okay. It's a good question. In fact, we search for first step. We want to search for compound with the interesting structure, and then we evaluate their linear and nonlinear optical properties. After that, we focus on maybe one or several compounds. We want to grow lasting crystal. For example, maybe wait for a minute. We can show. For potassium borate chloride, KBOC crystal. This compound is a perovskite related structure. We grow lasting crystal for KBOC. Where I found it? Wait for a minute. KBOC compound is found by Professor Belkonova. This compound has very interesting properties because it's wait for a minute. Here, yeah. This KBOC structure. This compound has very interesting properties. For example, its UV cutoff edge is about 175 nanometer around. And its SAG response is about 3 times that of KDP. And also, its bifurgence is about 0.047. Among the I mentioned, in general, the sugar bifurgence range from 0.04 to 0.1. It's suitable bifurgence. For this compound also has suitable bifurgence, 0.047. So this compound also can produce the UV cutoff around 272 nanometer laser wavelengths. So we grow lasting crystal. For potassium border chloride, as we know, the compound contains chloride. It means it's difficult to grow lasting crystal. It's easy to volatile for current atoms. So my students search for more than 400 flux system. They found one system. This flux system suitable for grow KBC crystal. This crystal, after grow lasting crystal, we cut the device and we use the in laser system and we produced the UV laser. Yeah, maybe in the future, maybe we can, be commercialized. We don't know. Anyway, grow lasting crystal is difficult. In fact, this time we want to search for experts, especially in Moscow State University, to help us to grow lasting crystal for ABF family, because the ABF family have very, very excellent linear properties. Yeah, thank you. Yeah.
Two ones.
Thank you.
First of all, you see there are some lead compounds you already showed to us. From this point of view, do you think maybe it will be effectual to show fundamental blocks from anionic-centric positions?
Fundamental building units?
The building units from anionic-centric positions, maybe it will be effective.
Yes.
Okay, and another question, so what is your opinion? How we can use this code like USPECH to predict the chemical composition for your compounds? It will be a useful tool or not?
Yeah, it's
maybe
a good question.
It's a question to the second lecture.
It's difficult. In fact, maybe...
Are there some
it's a challenge.
useful predictions?
Maybe next Professor Yang can make, will introduce his work about prediction. Yeah, it's a good question. It's a challenge in the world. Yeah, it's very difficult.
It's for plan for future, yes?
Probably, yeah. In fact, Professor Yang indeed design and make simulation and get this kind of material. Yeah, it's a very good question. Yeah. Thank you so much.
Okay, thank you.
Yes, thank you.
Another questions maybe? Okay, I think we'll start the second part of our meeting. And our second lecture is Chihoya Yan, and her lecture is about mechanism and design of deep nonlinear optical materials with tetrahedral structure units, please.
So, okay, thank you very much, and thank you very much for the kind invitation from MSU, and it's my great honor to stand here to show our recently result. So today's my topic is designing deep UV nonlinear optical materials with tetrahedral structure units. And I'm Zhihua Yang from Xinjiang Technical Institute and of Physics and Chemistry. So here I mainly want to discuss the mechanism and the properties for the tetrahedral structure units, and then we try to design a new structures which only contain tetrahedral units. So firstly, let me introduce, give a brief introduction for the nonlinear optics. Nonlinear optics appears when the strong electric field is induced by laser, so it can be reflected the susceptibilities here. This is called the second susceptibilities. And we can say that the polarization P nonlinearly depends on the electric field of the light. And the typical process here, we call it the second harmonic generation. We can say that this is a photon with the same frequency reacting to each other with the nonlinear materials and combined to generate a new photons. For the new photons, the frequency is the twice for the original frequency, and the energy also is twice. And here we can see that the wavelength is a half, so that means the frequency will be changed. For this kind of process, we can extend the wavelength for the laser. So for nowadays, it's a very hot spot to search the new nonlinear optical materials. So here we want to discuss the structure and the properties. So besides the symmetry and the components, usually we also want to try to find the fundamental structure units which can reflect the properties here. Because for the nonlinear materials, the properties here is very important. One is the birefringence, which means the optical anisotropy should be strong. And another is the SAG response, because the frequency conversion should be higher. And for the fundamental structures, usually for the scientists, they will consider the following several systems. One is the pi bonding here, BO3 or CO3 or other things, and also the lone pair effect, because it will bring the distorted structures also for the D10 configuration or D0 configuration. So typical nonlinear materials here, also there are phosphate, iodate, borate, or other kind of materials. And let's look at the wavelengths for this. And we can say that for the wavelengths, for the UV and the deep UV cutoff, deep UV region, we can say almost all of them are borate. So we can say borate is very important. And we also can say that in the deep UV region, only one compound, we just call it KBBF. So we can say that for the deep UV region, the requirement is very stringent because we should have a very large band gap. Also, that means the UV cutoff should be short. And another thing is we should have a large SAG response. But usually for these two kind of properties, they are contradiction. So we should make a balance between them. And another thing is the birefringence should be suitable. Suitable means not large, not small. So there has a region here. And for this suitable birefringence, usually maybe they will bring some layer tendency. In that case, the crystal cannot be grew as a large crystal. So it's just like you want a horse to run very fast, but you don't want it eat. And you also want this horse very handsome. So usually it's very hard to satisfy in one house, or here we set in one materials here. And usually we want to scan the structure units, and there are several units before we already discussed. So what kind of structure units can be chosen as a deep UV? We firstly check the first three structure units here. So firstly, we check the some long pair effect here, light, and there are some systems. For the first system, we can say there are also the isostructure. For the first system, the HEG enhancement is not higher, almost the same. But for the third system, we can say the SAG enhancement is very higher. It's almost 6 times that of isostructure for these compounds. So what's the reason for this? We can say that we found the orbitals for this microstructure, and it's a close lead-oxygen connection that will bring the more delocalized orbital. So this is will beneficial for the SAGG enhancement. But still, we have to check another thing. So for this kind of light oxygen, we will bring a strong stereochemical activity. So in that case, it will bring the red shift for this. So this is not good for the So this is not good for the deep UV region. So we checked for these 3 kind of structures. It's okay for the UV region and VIDA and infrared region, but it's not okay for the deep UV region. So here we can say that only for these kind of structures remained. So here I just list several crystals classified by the UV cutoff edge. So here there are different blocks classified the different wavelengths. We can say that almost of them are borates and also the carbonates, also the phosphate here. And also here phosphate. And for the basic structure, they contain the BO3, CO3, and also some BO4 or PO4. And we can say that for the shortest wavelengths here, so only these 2, they have the shortest cutoff edge. And for these 2 compounds, they only contain tetrahedral group. So actually, it is very reasonable because when we check the electronic energy level for the BO3, usually they has a downlink bond between the antibonding and the bonding energy. And for the BO4, the homolomal gap is very large. And in that case, we check the different compounds here. All these compounds only contain the tetrahedral units, and we can say that for the UV cutoff, they are less than the 200 nanometers. So they satisfy this deep UV region, the condition for the deep UV region. And for the SHG response, we can see that several of them satisfy this requirement. But for the birefringence, all of them very small. So that means usually for the compounds only with the tetrahedral group, they have a small birefringence, but birefringence is small, they cannot be used in the deep UV. This is a main question for that. So here there are some unclear mechanism. First one, usually for the microscopic stability for the tetrahedral units is very small. but also there are some compounds which has a very large SAG response. So what's the reason for this? Secondly, up to now, there is no central symmetric compounds with large SAG birefringence. So, but still there has some central symmetric compounds has a large birefringence. So what's the reason for this? And another thing is the design strategy, because all this group is a planar group. So it's very easy to make an alignment or coplanar. But for the tetrahedral group, maybe it's not so easy as compared to the planar group. So here we also know that for the tetrahedral group, it's very easy to grow large crystal because it's very easy to make a three-dimensional network, and also it's very beneficial to the large band gap. But the SAG response is unclear, and also the birefringence a little small. So based on this background, we want to discuss the mechanism or properties for the tetrahedral structure units. Firstly, I will introduce how can we calculate SAG coefficients. There are several theories here, and we mainly consider the second theory. And usually there are three kinds of process. One is a visual electronic process transition, and another is visual Hall transition. And also for the original formula, they said there is a two-band transition. So we firstly proved that for the two-band transition should be exactly zero. And secondly, we want to identify the contributions of atoms to optical properties, or separate the contributions of the cation and the anionic group. So the original method called the spheral atom cutting method. So for this cutting method, usually they will consider a radium. But how can we decide what's a radium? So this is a little problem for this. So another thing is also there are some space here we cannot count inside, and also it is not suitable for the covalent bond system here. So for this problem, we check the electronic density carefully. For the covalent bond, usually we can not easily to get the boundary for this. So based on this, we developed a new strategy to partition the atoms, use the Bethel's theory, and to make contributions for the atoms. For this new method, there is no artificial cutting radium and no residual space, and also suitable for the covalent bond atoms. So let's back to the tetrahedral group. Recently, there is some phosphates. We can see that for the tetrahedral group, usually the SAG response is smaller than the BO3, but still there are another reason for this. Here we can see that for these two compounds, this is boron phosphate. It has a large band gap and the large HZ response, but usually it cannot give a balance for this. What's the reason for this? Because usually the large band gap should have a small SAG response, but here still they has a large band gap and a large SAG response. So what's the reason for this? We checked very carefully for this, and we introduced some model here, and we found that the strong sp hybridization can enhance the SAG response. And also, besides the orbital hybridization, if we decrease the energy gap, or we also call it the charge transfer energy. We can also enhance the SAG response. So here we can introduce different contains to control this. So in that case, we design new new compounds, and for these new compounds, they have a good performance, and the SAG response is very higher. So up to now, in the phosphate, the SAG response is the highest. And we also check the other tetrahedral group, and also Professor Pan already discussed for BOF. This kind of tetrahedral is a new nonlinear active units, and also there are some other kind of tetrahedral. They are good for the SAG response. And another thing is birefringence, as we discussed before, that we can enhance the hybridization to enhance the SAG response. But can we ensure the birefringence? This is the main problem for this. So for the planar group, we can easily to make a planar arrangement or the coaxial arrangement to ensure the larger birefringence. But for the tetrahedral, we can say for the three compounds here, we cannot say exactly what's the regular region for this, and which one has a larger birefringence may be the problem for this. So for this, we proposed a new method and to try to explain the reason for this. And we found that for the birefringence, it's a proportion to a response electronic density difference here. And for this, we give a explanation for why for this compound has very large birefringence, and for the borophosphate has a very small birefringence. So the main case is this index. We just call it IEDA index here. And also we can see that the tetrahedral group has a very higher contributions. Also here, we check the birefringence with this key factor, they are proportion to each other, and also the calculation birefringence, and this is experiment, they are consistent with each other. So for this, we can adjust this important factor and to enhance the birefringence. And based on the mechanisms for this, and we try to design the new structures which only contain the tetrahedral group. So firstly, for scientists, usually they have several methods for this. One is they scanning the exist structures from based on the database, and then they calculate and tell the experiment which one is good, which one is not good. Another one is make a substitution. This can be do the experimental, or this can be done theoretically. And also there for the structure things, for example, from Professor Bagnova to predict new structures based on topology, symmetry, analysis, or other things. And also, they have the global optimization method. For example, WOSPECT, or also maybe they call the USPECT, and to predict new structures. And this is a very powerful method and unbiased method. Also, with the help of WOSPECT, we predict the new structures, and this is several for that. And here, actually, I will not discuss how to predict new structure, use the WOSPECT. Here we want to say, can we consider from the active units and such a function modulus and break the symmetry and to design the new structures. So firstly, we back to the tetrahedron. And because we know that for this this kin factor is very important for the birefringence. So we try to identify this kin factor, and we make a rotation for this. And we can see for this picture, if the kin factor is very high, that means the birefringence is higher. So we can say for what kind of tetrahedra should have a large SAG response. And there are two compounds as a comparison. And these compounds, because the theta is not so easy and is changed. And for these compounds, the theta is 0, and this make largest birefringence for this. So we call this kind of arrangement is a zippo arrangement. So, but this zippo arrangement only exists in the central symmetric. Can we transplant to the non-central symmetric? So for this, we induce the different cations here. Also the octahedral units inside, and we break the symmetry, and from the central symmetric to non-central symmetric, and we find the 50 compounds here, and 12 of them are non-central symmetric, and 3 of them are central symmetric, and we checked all the susceptibilities for the new structures. They all thermal stabilities, and we found that these compounds is very good. So we checked again the stabilities is dynamic stable, also they are thermal stable. And we check the properties for these new structures. We can see that these new structures satisfying the requirement for deep UV region. So it is promising materials with the shortest phase matching wavelengths and the largest birefringence in the non-central symmetric phosphate up to now. So here is my conclusion. And so we check the tetrahedral group, and usually this tetrahedral group sometimes is ignited, and we check the mechanism for them, and also we try to design new structures, and hopefully maybe in the tetrahedral group they can extend in the new next UV or deep UV materials for this. And another thing is, in future we also want to make a mixture between them, because as we know, the prediction from the global minimum will take time, and we want to make also for the regional design, usually it depends on experience or mechanism for that. So whether we can make a mixture together and shave time, and efficiently we can design new structures for this. And finally, I want to thank my group leader, Professor Pan, for all the support and all the collaborations from different universities, and also the students, Lei Binghua, and so on. And thank you for attention.
Thanks. You have said about hot point. I saw it in your picture as a vanadate tetrahedron. What can you add to this as an example of perspective vanadates in your research? Vanadate group are known to be is a structure with phosphate.
Yeah. Yes.
It has a larger covalency, and it has more nonlinear susceptibility, I believe.
Yes, thank you so much. For the, let me check, it's here, right? For the oxy4 is a very hot spot, and we check that the SCG response is higher. But usually the band gap is not good for deep UV region. So usually for the deep UV region, we will not consider for this kind of units. But still, it's very important for the visible region. Yeah, thank you.
Okay. Any other questions, please?
How will you find global minima in design structure? Will it be quantum chemistry or some mechanics-like optimization?
Yeah, thank you for the question.
First part of the question. Quantum chemistry or something?
Same empirical.
So what kind of method do we use for the prediction?
Yes.
Yeah, so there are several methods. Here we use the USPECT and from Professor Ognauf, and we will, several methods, we will consider maybe one compound, and also we can change the original part, like if we want to predict new structures as lithium, boron, oxygen. We can make a lithium oxide plus boron oxide, and change the number for this, and we can predict many new structures for this.
And this is really a question. There is a known problem of multiple minima. That is, when you make calculation, you are paying much more minima of almost the same depth, almost the same energy, then you have real crystal structures or polymorphs of the same compound. How will you plan to overcome this problem? The problem of multiple minima.
So you mean how to find the minimal?
There is a well-known problem. Then when one performs structural optimization, it usually gives many
Local minimums.
many different minima, many different structures of almost the same energy.
Yes.
Some of them correspond to a real structure, the other one are exceptional. What will you do to avoid this problem?
You mean if there are several compounds, several structures almost with the same energy?
Close energy.
Close energy. How can we identify which one is?
Yes, how will you choose the real global minimum?
Actually, we firstly we consider as energy. This is the first thing. But if almost similar, maybe we can call it. So we will consider almost we will consider all of them, and also we have to check, because this is energy minimum. We also have to check the dynamic stability and the thermal stability, and then we will to predict the properties, and then we check which one is okay.
Another questions, please? I have also some. The continuation of this question. During your USPECT calculations, you use only ab initio procedures at all stages, or the first stage of generation, first structures, you use force field methods? Or only ab initio calculations you use during the evolution research?
You mean we change the variation of the component?
During your calculations using USPECT code,
yes.
You use only ab initio codes?
Or ab initio?
Or sometimes at the first stages semi-empirical potential?
Yeah, yeah.
Yes or not?
Please repeat.
Okay,
Sorry
maybe
for-
later in the discussion.
Yeah.
And another question. I have seen that when you tested phosphates, you use only xenotime structure type for heavy rare earth elements. Do you test it also monazite structure type for light rare earth elements or not?
You mean the light element?
Yes, for another structure type for
Another structure type.
not
you-
xenotype with 8 coordination, but 9 coordinated rare earth element.
Yes. So nowadays also we try for the light elements and to keep this kind of arrangement. But
Okay.
we are not sure that this is a stable structure or not. But we are trying for make a design for this.
Okay, thank you.
Thank you.
Another questions, please. Okay, I think that
Thank you
questions
so much. Thank you.
we have no. So our mini conference, I think that the scientific part is closed. Thank you very much for attention. Thank you.